Welcome back to Think Design Work Smart. I'm Alex Bolboaca and I'm coming at you from the Mozaic Works studios. And what I have for you today is a rethinking of fundamentals of software design. I'm gonna give a short presentation regarding some of the fundamentals of software design as I see them, as I understand them, and as I understand them in contrast and in comparison with other design disciplines. I believe that the software design discipline has been largely either tried to use the wrong metaphor or failed to connect with the past experiences in design. And to me, I believe there's huge value in reconnecting our design discipline with the existing design disciplines. And it so happens that I've read a bunch of books and I thought this through for a number of years. And this is just let's say the tip of the iceberg, what we will discuss today, but I hope it will be interesting enough. And I've seen comments from you saying that you are interested in design topics. So here it is. And I hope you'll find this interesting. First of all, let's talk about the metaphors that we are using. And the metaphor that we've been using for a long time when it comes to software design and software architecture has been the metaphor of construction. We've been talking about making architecture and architecture documents and designing architecture and all kinds of things. And I think that we've missed the point with this one because construction is different. And in order to make this easier, I think that the right metaphor is different. And think about the image on the right, which is the build. So when you build a car, what does it take for us to start building a new car model? Well, somebody needs to do the design phase and come up with some blueprints. And then based on those blueprints, production line is built, the robots are installed and all these things. And you are using the production line in a factory in order to build the car. And that's how you do large-scale production. So you build maybe hundreds of thousands, millions of cars. In our case, however, building millions of software products of the same thing is basically just you build once and then you copy. And so the question is, where does the metaphor come in? And the build that we are doing, the production line, is actually what our IDE, what our compiler, what our interpreter is doing. And what we are really doing is creating the blueprint. So the phase that comes before the actual build phase. Only in our case, the blueprint doesn't look like a bunch of drawings with measurements and all kind of technical details. Our blueprint looks like instructions, code that fundamentally is encoding knowledge. And based on that, the compiler can build the right thing. So what this means is that our jobs are more likely the jobs of car designers than more like the job of a building constructor or a building architect. So what we are really doing is structuring code, okay? Which leads us to our And my favorite definition for software design, and I'm going to make a distinction between software design as result and software design as process. So software design as result is the code structure that optimizes for certain desirable characteristics. And usually the most important characteristic that we want is changeability. Why? Because we are building software. The difference between software and hardware is the software is malleable. Hardware is not. Or at least that's how it used to be. Now, because a lot of hardware is also software, it becomes more malleable, and we get these kind of worlds that come together. But in general, what we have is software design. You know, what we want is changeability to be one of the most important characteristics. We want to be able to add new features. We want to be able to improve existing features and so on, and to add different behaviors, all that jazz. And we want to be able to fix bugs, errors that come out of the design process. This is basically what we are doing. Now, software design as a process is the act of producing this code structure. And basically you can see it in two ways. You can see something that you need to do before, or something that you need to do during, or rarely, although it's quite often, something that you need to do after as a process. What might this process entail? Let's think a little bit about what it takes for a car designer to build a new car model, and to design actually a new car model. What would they do? Well, they would probably make some drawings. They might build some prototypes. So with the help of a team, they might build a prototype car to test various materials, engine, the power, output, various things that you need to test for a car. So what would the software design process entail? Similar things. We might make some diagrams, write some code that proves that our design ideas work. So do some prototypes. Anything goes here. So the design process can be anything from we start with a little bit of code and then we keep modifying it, or it can be we draw diagrams, or it can be somebody who sits in a corner and just thinks about the design and then comes up with a solution. And I think various people can do these things in different ways, and they are all good as long as the result is good. So I'm not against people doing design differently than how I do it, which is through test-driven development, through an incremental process. However, we need to understand that design is necessarily an iterative process. So you will never be able, or okay, maybe not never, you will very rarely be able to come up with a solution that works precisely as it's required from the very beginning, and that is structured appropriately. So what you need to do is to iterate. Now, there are various times when you can iterate. You can iterate before writing the first line of code. You can iterate by writing some code that you throw away afterwards. You can iterate by writing code and then incrementally changing it and improving it. Or you can iterate by making something work and then going back and doing a second pass where you refactor and make a bunch of things. And depending on, when you iterate before writing code is what we usually call upfront design, and is generally frowned upon to have big design upfront because we had a lot of problems with that. But the main problem is actually not when you do the design, but it's more what is the design feedback loop and how fast it is. Because that's the main problem. The main problem with big design upfront is that the feedback comes very late in the process. If you do, 3 months of design and then you implement for 6 months and then you get the feedback, it's very late and it's very difficult to fix it. So this is why we prefer, or I prefer, in general, it's preferable to reduce the feedback loop, to have feedback as fast as possible. And since we have this advantage of code as an executable medium, we can actually use this to our advantage and, write code, see that it works, improve it, write some more code, see that it works, improve it. And this is basically what you're doing when you're doing test-driven development. Only slightly different in the sense that you first define what you want to solve and then you write the code and then you improve it. So again, if you iterate before writing code, I don't see a problem with that as long as your results are good. Because if you iterate before you write the code and maybe you get some feedback and you do a lot of iterations here, but then you actually implement the code, but then you realize that you need to refactor and to fix things, you've introduced errors in the process. You've introduced defects in the design, right? And so in general, when we have such an issue, it's better to go into smaller steps and get faster feedback. And that's where things like refactoring, test-driven development, particularly test-driven development, can really help. And just to be clear, test-driven development, despite its name, is a design method. It's a method for incremental design. Because what you do is you start with a problem, you split the problem into smaller problems, and then for each smaller problem, you write a test that fails, you implement the simplest code that would make it pass, and then you refactor and you repeat this process. Now, even when you do TDD, you might do some prototyping. This is perhaps another misunderstanding. Remember, the goal is to design. We use whatever we can. So even if we use TDD, sometimes we might not know what is the right next problem. Or we might not know how to fundamentally solve a specific problem. And when we are in a complete unknown, it's good to stop and do an iteration of when you prototype certain things or you document yourself, maybe you find a specific algorithm that would work for that problem and so on. So don't imagine that if you're doing test-driven development, it will just be red-green refactor. Sometimes you'll have to do other things. And I think we've discussed about this in length when we commented on Kent Beck's Canon TDD. I advise you to watch that video if you haven't yet. Okay, and then the next thing about design, which is a relatively new development, has been the introduction of UX. And initially it was ergonomics, then usability, and then UX. So UX refers, it means user experience. And what it basically means is, how about we optimize design for users, because happy users are more productive and more likely to promote your product. And this is where success of some large companies have come from, like Apple. Apple has invested a lot in usability and it worked, and in UX, right? And it really worked, and that's why we have a bunch of companies focusing on, and a bunch of roles that focus on UX. But this improvement has largely avoided software design. Only recently we started talking about developer experience, and I started talking before this about usable software design. And usable software design takes into account that the operator, the user of software design, you can call it the operator, is the programmer. So then the question is, how do we optimize? How do we optimize the code structures such that the programmer, the experience of the programmer is good? And there are multiple reasons for that. One of them is happy users, but another one is avoiding mistakes. This has been a big problem, particularly for operators of industrial systems, industrial control systems, like, for example, a nuclear plant, a nuclear power plant. Operators of a nuclear power plant control systems are very well trained. They know a lot about the problem domain and so on. But the systems could still trick them into doing the wrong things, which could have catastrophic results. So because of this, it's useful to ensure that you design the systems in such a way so that users are less likely to make mistakes. Now, do you see the parallel here? When do programmers make mistakes? Well, we call those mistakes bugs in programming, but there are areas of the code and ways of structuring and of writing the code that promote mistakes. And we should be able to largely avoid those. And this is the general thinking. On the other hand, having happy programmers in your team, how many of you, when you go and start working on your code base, are happy making changes and you feel free and creative and so on? I think many programmers have a very different experience for that. Usually it's a chore to change software, to change code, particularly in large systems. So maybe it might be a good idea to look at programmer experience, because happy programmers are more productive, they will avoid mistakes, they will come with better ideas and so on. So why not? Okay, and this brings us to two resources that I want to focus on, because I think these are very, very interesting. They are quite related in a way. First of one is a picture that I saw posted on Twitter, and I will post the link in the description. It's called Laws of UX, and I'm gonna do a deep dive into these laws of UX and see how they apply to code, because we might see some interesting parallels. Another one that I'm not gonna go into, but maybe I will leave for a future video, is called Universal. It's a book called Universal Principles of Design 100 ways to enhance usability, influence perception, increase appeal, make better design decisions, and teaching through design. And I have actually studied this book a lot, because what I wanted to see is any of those principles applicable to software design, and how. And I managed to find quite a lot of parallels, and I have a bunch of notes on this book. So if you are interested, yeah, by all means, it might be a cool thing to look at. But for now, let's look at this one, Laws of UX. And remember that these are particular for the usability and user experience when it comes to applications. So they will use language that refers to graphic components. However, what's very interesting is that we can look at these in different ways once we think about software design like I framed until now. First one, aesthetic usability effect. Users often perceive aesthetically pleasing design as design that's more usable. So this is interesting. Aesthetics is not something that we think about as programmers. And I think it's a pity. Actually, we often joke about, this is code, this is not art, or something along those lines. And look, I understand this. On the other hand, what I have to say is aesthetic, even though you think it doesn't matter, it actually matters. So there are a few interesting things that I done around this. One of them is to try different fonts for my ID. I tried using the Garamond fonts and serif fonts and things like that. And with each type of font, you have a different feeling about the code, which is very, very interesting. And I think we could do better with organizing code with better typography. And really, there's a lot of work to be done here, and yeah, there were some experiments around this. One thing that would be very interesting is to have your code structured in, the function to be the class to be a title, the class name to be like a title in an article, and then to have paragraphs that are, or sections that are function names, and then paragraphs that show the code. And maybe even with those different font types, which is apparently still not supported by many IDEs. So, but there are a few things that we can do with aesthetics. For example, one of the things is the use of white space. We could, and it's something that I do, I leave empty lines between paragraphs of code, let's say. One example here is in tests between given, when, then, or act, arrange, act, and assert phases. I leave an empty line in order to visually separate this. I try to have everything as low indentation as possible, and so on. Those are very limited, but they give a sense of structure, and at least it makes you feel slightly better when you see code that is structured than when you see code that is kind of all over the place with a lot of indentations and a lot of... So yeah, maybe there's something to be said here. Doherty threshold, productivity soars when a computer and its users interact at a pace less than 400 milliseconds that ensure that neither has to wait on the other. Very interesting. This is a psychological effect. So what we want is to have immediate feedback from our code. Now, part of it will be the IDE. When you type, you want under 400 milliseconds to see potential code completions and things like this. But think about what this says about our tests. So ideally, I should be able to, and this is something that I've done, make a change, save the file, tests automatically ran, and they tell me whether it's green or red. And this whole process should happen under 400 milliseconds. This would be the ideal. Now, how do you do this? Depends a lot on the technology that you are using. If you are doing this in a very large code base, what you need to do is to select tests that fit the part of code that you are working on, because otherwise they will be very slow. But this is something that would be really, really cool to have. And as far as I know, it's not as easy to do with IDs. I mean, what I'd like to do in an IDE is to be able to go to a file, and maybe it could even detect these are the tests that we need to run, and just automatically run them after each change, and have this just be an option. No. This would be really cool. And in an IDE, it could run in the background. They could do a lot of optimization and all kinds of things. This was particularly difficult to do in Java because it took some time to initialize the tests. Well, it was Grails or Spring Boot, kind of the same thing. But you could improve that with, they had some caching mechanisms and, keeping the testing process as a daemon in memory that would run the different tests. So there were ways of optimizing beyond loading and initializing for the first time the JVM. Fitts law. The time to acquire a target is a function of the distance to and size of the target. This is very useful, for example, when you think in terms of visual elements. If you want people to hit a button, how easy it is for them to hit that button depends on how far the cursor is and how large is the button. What does this mean for software design? Well, let's think about the situations where you need to modify some code. And maybe you don't remember exactly where you need to go. So in that case, acquiring a target is a function of how far it is, and how far can it be? Well, do you need to click through multiple files together? No. And the size, in this case, we don't really have sizes. Everything is the same size, whether it's a class or a function or a module. I think we perceive them all as being the same size. So the size being equal, the distance is the difference. And the shortest distance is when you can go into your IDE and type a partial name for the thing that you are looking for. And ideally the first result is the one that you're looking for, but it could be, I don't know, the 5th, maybe the 10th, but not more than that. because after that the distance increases. Yeah, so interesting thing. Postal's law: be liberal in what you accept and conservative in what you send. This is almost HTML, HTTP API design things. It's a very good principle, and in general for classes, although I would have to say I'd prefer that we don't accept nulls and we don't send nulls. But other than that, it's a good principle in general, and I like it. So the way I apply this is through hidden types. I don't like to write types for the parameters of functions and for what functions return, because what I want to have is to be liberal in what I accept. But then what I send or what I return from the function is always a data structure that's well defined. But if I get a parameter that has a, I don't know, a plus method, I don't care whether it's a number or a string or something else. It's just something that has a plus method. And there are ways of doing this with strongly typed programming languages. But for me, I prefer to just accept, without any type. Goal gradient effect: the tendency to approach a goal increases with proximity to the goal. Right. So the tendency to approach a goal increases with proximity to the goal. This is interesting. I haven't thought about this, honestly. I don't know how it would apply. I'm sure I will get something at some point. Hicks' law. This is very interesting. The time it takes to make a decision increases with the number and complexity of choices. So think about it this way. You have a task to implement. You have a requirement. You need to implement something new in your code. How many potential choices do you have for where you place the different components of the solution? Because it will take you longer the more options you have. So paradoxically, it's better to have constraints on the way we structure our code if we want to move faster and to be more productive. What could such constraints be? Well, one such constraint could be, and actually let me give you an example. If you're doing an MVC type web application, you could have constraints on in controller, just place 2 lines of code, one that calls, or a few lines of code, one that validates the input, one that calls a service to perform an operation, and one that returns the view. And that's it. And then you have a type of service that does a specific thing, and then you have another type of class that has that is an entity type class. And maybe you have a query that searches entities into the data store and returns them, and then you have a command that stores data in the data store. And you might have a validator that validates the different parameters. So, and these are patterns, design patterns, but design patterns that you create for a specific context. And this is very powerful. So remember, if you have too many choices to make when implementing a solution, I know programmers believe that this is a function of creativity, or some programmers, but in reality it just slows you down. Figure out a few general laws and that apply in 80% of your for 80% of your tasks, and then leave the other 20% for the situations where you'll need to define new patterns, or maybe find them through practice by implementing a first solution and then figuring out how to refine them. And this just makes the development faster. Jacob's law: users spend most of their times on other sites. This means that users prefer your site to work the same way as all the other sites they already know. Now, this is slightly more difficult to apply to software development. It only applies it would apply if you would have outside contributors to your project, to your code base, that are used to working in other code bases. So maybe it applies more to open source. And in that case, they would prefer to have, like if you're working in a Java environment, you'd prefer it to work the same as it works in all the other Java environments. Like it has a Maven file, it has a, all that set of all the set of tools that is specific to a Java, but less so in our case. Serial position effects: users have a propensity to best remember the first and last items in a series. Yeah. Again, slightly difficult to apply in software development. Maybe about the first and last line in a function, although it's not really correct because we kind of focus on chunks. So, law of common origin: elements tend to be perceived into groups if they are sharing an area with a clearly defined boundary. Yeah, and this is maybe the way you see your code in your IDE. If you see multiple functions, you'd perceive them as being part of a class. But again, this is something that we largely train for, whether we want or not. This one is much more interesting. Law of proximity: objects that are near or proximate to each other tend to be grouped together. So this is why it's very useful to organize functions inside the class based on the relations between them. So if I have a higher level function that's public that calls low level functions that are maybe private, I like the higher level functions to be here and then proxy to be close to the smaller functions that are used. Now this gets a bit more difficult if you have multiple public functions that use different combinations of the private functions. And it's never a perfect way of organizing, but it's worth keeping in mind when organizing your code. Let's see a few others. The human eye tends to perceive law of similarity. The human eye tends to perceive similar elements in a design as a complete picture, shape, or group, even if those elements are separated. So if you have similar elements, this is maybe a different thing. I think that many developers have a similarity detector that can detect similar code in different parts of the code base. And this helps us because what we try to do is to largely remove that similarity for better changeability. Is the don't repeat yourself principle. But it's interesting because I've noticed most programmers tend to see where there is copy-pasted code, but it's more difficult to see beyond that other types of similarity, like numbers. Is the same number appearing in different places, or constants? So I think it has some limits, and it talks about the human eye, how we perceive similar elements in the design. We work with text, which is slightly more complex, and so I think there are additional cognitive processes other than just what you perceive initially through the eyes. The brain comes in and does some more stuff and kind of chunks together different things. So you probably need to develop this ability to see similarities in code beyond just copy-pasted things. This one is very, very interesting. And actually these last two. Miller's law. The average person can only keep 7 plus or minus 2 items in their working memory. Why is this important? Well, it's more or less, it's true, but it's also slightly misleading. Because the working memory also works based on chunks. What I mean by that is you can see a class, and inside of a class you have 7 methods. And you can probably remember all the 7 methods while you look at the class. But then you can also remember 7 classes without necessarily remembering all the functions that are in the 7 classes, but you can remember them at a higher level. So, and in this case, the methods are chunked in the classes. They become a higher level structure in your brain. And you can see this in various ways. I mean, this is why hierarchical structures work, because, you know, if you have a document, you can remember 7 different documents, and then if you think about one document, maybe you remember the 7 chapters, and if you think about one chapter, you might remember 3 ideas from the chapter, and so on. So it works in chunks, but it takes some time to change the context from one chunk to another, if it makes any sense. So yeah, so this is 7 plus minus 2 rule. Very interesting. And the last one, Tesler's law, also known as the law of conservation of complexity, states that for any system there is a certain amount of complexity which cannot be reduced. Yeah. So remember this. If you ever struggle with complexity in your code base, the question is, as Fred Brooks put it so well many years ago, the question is this accidental complexity or is this essential complexity? Essential complexity is the complexity of the problem that you are solving. And no matter how you structure your code, and even if you had the perfect technology, the perfect code structure, you would still have that complexity. There's no way around it. Accidental complexity is the type of complexity that you could remove, but that comes from technology, from the way the code was structured, from lack of knowledge. Maybe you didn't know how to solve the problem best when you first started. Now you know better. And then you have technical debt. That's the original meaning of technical debt. But remember that what you want to do ideally is to get as close to the essential complexity as possible and remove as much of the accidental complexity. And that's the most important part. All right, so this is like a quick dive into how the laws of UX apply to software development and software design. And this book is also, as I said, a very interesting universal principles of design. I found many things that apply to software design there, and they are very, very cool. And I can definitely do a deeper dive into these ideas if you find them interesting. So what do you think about this whole talk today? I hope this opened your eyes to what design, software design can be and how you can approach it in different ways. And I hope that you will have interesting ideas based on this discussion. And if you get interesting idea, leave us some comments. Let us know what you are thinking. And if you have any questions, let us know what they are. And if you have any suggestions for what else to talk about related to software design, let us know. I'd like to know this, and I like to get in touch with you and provide useful topics that you find interesting. With this being said, as usual, thank you kindly for the view, and until next time, remember to think, design, and work smart.